Hello and welcome back to Calculus1. I don't know which one is anymore. It's been 3 months of this constantly, so is this working? Yes. Hello and welcome back to Calculus1, section 5.1, or Approximating Area under a Curve. And what does it mean? Well, I just want to know what the area of the entire thing over here is. And we can approximate it by simply picking this point and picking this point here, just, strike the line through. There we go. And you have some kind of trapezoid here that you can quickly compute, and you're done, right? Except there is this error here that is bothering us. And it seems to be large error. So can we do this in a nice way so it's still easy calculations, but not have as much error? And the answer is obviously yes. What we are going to do is we are going to divide this into these vertical strips like this. And then we can use the left corner touching the function to create rectangles. Now, I understand that there is error here. These are all error, right? Which we can mitigate and we can improve on, we'll see, by picking more of these rectangles and things like that. But let's deal with this first. So what do I have? Well, I have my partition x0, x1, x2. These are all values on x-axis, right? Where x0 is a and x4 is b, which makes each one of these delta x, and they're evenly spaced for convenience, right? Delta x would be the width of each one of these, because delta x is given by x1 minus x0, which is the same as x2 minus x1, which is equal to, and then I'll just put 3 dots for the rest. It's okay. So what do we do? Well, I am going to use left corners to compute function values which would give me the height of each rectangle and multiply by the width delta x to come up with the area of each of the rectangles. So I'm going to use f of x0 times delta x as the area of the first rectangle, plus f of x1 times delta x for the area of the second rectangle. So these are rectangles 1, 2, 3, and 4. So this is number 1, this is number 2, plus f of x2 delta x for area number 3, and then plus f of x3 times delta x for rectangle number 4 for area. Now you can quickly see that the true area is approximated by area L. I use L because it's the left rectangles. Why do I call them left rectangles? Because I used, you see how if you pick any one of these, right? Pick the first one over here. It has a point here and a point here. So you have a left and a right point. So you can draw your rectangle from the left or from the right. So that's what the left and right is all about. So area on the left is going to be equal to delta x times, and now in parentheses over here we have f of x0 plus f of x1 plus f of x2 plus f of x3. 1, 2, 3, 4 calculations, 4 rectangles, so we're good to go. This is a formula when n equals to 4. N is the number of rectangles. We can also have the right sums. I am computing again between A and B area, and what I'm going to do this time around, I'm going to divide this and use right sums. So now I still have the same x0, x1, x2, x3, x4 divisions. And that helps me keep track which value I'm supposed to pick up, right? Delta x is still the same everywhere, delta x. And now, if you are looking at the area from the right, I mean from the right points, we would have f of x1 to be the first one times delta x plus f of x2 times delta x plus f of x3 times delta x, and finally f of x4 delta x. So now true area is approximated by area with the right-hand sums, I mean right-hand rectangles, and what I have is factor out delta x, and we have f of x1 plus f of x2 plus f of x3 plus f of x4. So this might look intimidating or whatever, but this is literally middle school level. Let's try this on area under f of x equals square root of x on the interval, let's say 3 to 7. There we go. So this is the question. And what I can do is graph, partition, and then move from there. Now I know the square root of x is not going to go on the left-hand side, so I can just draw this and then go into this square root graph. Now interval 3 to 7. Well, here's 3, 4, 5, 6, 7, right here. So this is your interval 3 to 7. So what do we want to know? We want to know that area of that trapezoid-looking, right? Trapezoid-looking function. Now, shape. I mean, now, you know, making a straight line here, like that, would actually give you a pretty good approximation, right? But then we can also subdivide this at each unit 1, making delta x to be 1, which actually gets you, in this case, 4 rectangles. So delta x is 1. Let's use left. So the area that we are going to get is going to be lower than the actual area. So area is approximated by area at the left, which is going to be delta x times so these are my x0, x1, x2, x3, x4. So I have delta x times, and I just have, since I'm using the left ones, right? I'm using the left ones because the left corner of each rectangle is touching the function. I have my f of x0 plus f of x1. Now, can you do this using the right ones? Sure. I'm going to get a different number, but plus f of x2 plus f of x3. So delta x is 1. And now, since I'm using a square root function, I see the x0 is 3. So all I need to do is to say square root of 3, oops, plus square root of 4, plus square root of 5. 1, 2, 3, 4. 1, 2, 3, 4, square root of 6. Because you're labeled over here 4, 5, 6, and 7. So now we can actually use the calculator, figure this thing out. So the calculator says square root of 3, close parenthesis, plus 2, plus square root of 5, close parenthesis, plus square root of 6, close parenthesis. So that's 8.42, about. So area is about 8.42. I can check what the exact area is, that just to see how close this is. So the Wolfram Alpha answer says that area is equal to 8.883. And we have, by working on middle school math, we have 8.42. I'm happy with that. Right? So when you want to approximate area under the curve, you slice that area into these strips. Each strip becomes a rectangle as soon as you decide which way you want to draw that rectangle. You have the left rectangle, which would be from the left point, or you can do the right rectangle from the right point, which is the blue one. You see that all of the blue ones, in this case, all of the blue ones are going to overshoot the area. If you have all the red ones, they're going to undershoot, right? There is a way to fix that as well, but you can calculate left and you can calculate the right and then just say, well, the area is somewhere in between. And that's cool too. So please don't make this difficult and don't make it something special or big. It's as simple as this. Each one of these is a rectangle. Area of the rectangle is width times the height, or width times the length, or whatever you want to call it. You have delta x here, which is the distance between two numbers. Doesn't have to be at 1. It could be half, could be whatever. And the height is calculated by simply calculating the point in the function. That gives you the height of 0, right? Move the numbers. Delta x times that plus delta x times this one, delta x, delta x. Yes?
So could you get closer to the actual answer if you did it right?
Yes.
Also, is there a way to do the exact answer without a computer?
Yes. 5.2. That's next section. There'll be plenty of time for you to regret it and the question. How do we make this better? I use more rectangles. Because when I use more rectangles, the error gets reduced. Let me draw a large picture here and say that I am, right, so this is enlarged. And I have a rectangle that was the left side rectangle, and we just do this, right? So there is f of x here, and there's delta x here, and so on. Now, what happens? We see that all of this is error, right? All of that is error. Are we all clear on that? Because the area that you're computing is right here, and the function is all the way up there. So this little pizza slice, or whatever you're going to call it, is going to be error. Now look what I'm going to do. I'm going to actually cut this in half. That means I placed twice as many rectangles. And now, when I draw the rectangle there, this piece over here is no longer error. Do we all see that? Error is just here and here. So is my answer better? Of course it's better. But what's the issue now? What have I just done?
It's twice as long.
It's twice as many calculations, right? There's no free lunch. There's no free lunch. So I am doubling my calculations, and I am eliminating a lot of error. Can I eliminate even more error? Sure. Cut each one of these in half. Add even more. Come on.
You do that infinitely.
And that's how we get exact. So cut this in half. Draw the rectangles over here. And look at that now. Your error are now, so now this is no longer error. This is no longer error. This is no longer error. So a lot of stuff is no longer error. So increasing the number of rectangles gives us better approximation. Good. Can I achieve exact? The answer is yes if I use infinitely many rectangles, because infinitely many rectangles will be infinitely thin and they would fit everywhere without error. Therefore, when you add all of those infinitely thin, whichever we are going to do tonight, so don't, right, relax. I'm going to write the formula for delta x. Delta x is b minus a over n. So you know that AB is the interval and n is the number of rectangles. So that formula will follow us. Midpoint approximation. Now this is a really cool one. we have our function. And let's say we're going from here to, well, you know what, let's do this. We start A, so let's go x0, x1, x2, x3, from A to B. The rest of the universe doesn't exist, we just have A to B, that's all we care about. So now, what's the midpoint calculation? Midpoint calculation tells you to go in the middle, and then go up, and wherever you hit the function, that's where the rectangle goes. Go from the middle up, and wherever it hits, draw rectangle. And the last one. And that's it. So now, what are these values at which we are computing function? Well, it's going to be average of x0 plus x1 divided by 2. That's what it is. It's a simple average. So if these numbers are, 1, 2, 3, 4, and so on, then 1.5. That's what it is, right? I want to work out a midpoint problem, and let's say approximate area under, and now we put some function here. What should I put? Area under y equals 1 plus ln x on 1, 2, 4, using n equals let's go with the 3 rectangles. You know what? I want to use 5 rectangles because it's bad. This is going to create terrible numbers, but we can deal with terrible numbers. This is a numeric section, so you are programming computer to do this stuff for you, obviously. N equals 5. I picked the worst possible number. I mean, you can do worse. I have complete confidence. So, what do I have? The graph really doesn't matter as long as you have some kind of, curve there, and we start at 1, we know ln starts there at 1. And then I'm going to draw 5 of these. So 1, 2, 3, 4, 5. So that's my x0, x1, x2, x3, x4, and x5. And x5 is where the 4 is, and x1 is where the 1 is. So now remember what we're doing. We go in the middle, and we draw the rectangle. Go in the middle, draw the rectangle. Go in the middle, draw the rectangle. The middle, there we go. And the last one is pretty much flat. Good. Please note that when you single out one of these, whatever your, I totally missed this. Fixed. So whatever you add as extra area, well, not whatever, but pretty close, right? You see how it balances out. It doesn't balance out 100%, but on one side you overshoot, the other one you undershoot, and they don't cancel completely, but they cancel up to some point. No.
Well, not efficient, like
there's
accurate.
Definitely no, and no. Like they're all no's. All of them. So now, what am I going to do? Well, I have to compute all of these values. So first off, I have to know what my x0, x1, x2, and so on are. So that's going to be my delta x calculation as b minus a over n. My b is 4, my a is 1, and n is 5. So this is 3/5. 3/5. Now 3/5 is 0. Very good, 6. So what are my x1 and the rest? 1.6, 2.2, 2.8, plus 6, 3.4, and then you see plus 6.6 will be 4. So it matches, right, as you put those numbers there. Am I computing my functions at these numbers? No, because I moved to the midpoint. Great, right? So what do? To find the first calculation here, that will be f computed at x0 plus x1 over 2, and then times delta x to find the area for the first. So what is the first rectangle? So what is the function? Needs to be computed at x0 plus x1, so that's 1.6. No, it's 1 plus 1.6 divided by, what do we have? 2. And then delta x is 3 over 5. When we are done, we still have to deal with that. So I have ln, because that's my function, right? 1 plus ln. Oops. So now, 1 plus ln of x is going to approximately be equal to, and you just need to compute this stuff. So it's a function which is we have as 1 plus ln x. But instead of x, I'm going to place the value from here, which is 2.61.3. So this is 1 plus ln, that's a function of all of this mess, and then times so all of this times 3/5, and that's it, because that's your delta x. You compute this 4 times, right? So 1 plus ln of 1.3 times 0.6. So it's going to give me roughly 1.157. And I cut off all the other decimals there. So I am able to compute the first rectangle, right? And then you go and you compute the second, then the third, and the fourth, right? And then you just add those together. So for the second rectangle, what do I have? I have the midpoint at x1 plus x2 over 2 times delta x, right? So that's going to be our 1 plus ln. And now the value here is 1.6 plus, that's 3.8, right? 3.8 divide by 2, we get 1.9. So we are looking this for 1.9. with a 3/5 times 3/5, and that's going to give us a number. I'll just put the, just do it. So this is it. There are more techniques that you will learn in Calc 2. Trapezoid rule, Simpson rule, right? If you go higher in math, cubic splunk, right, for cubes. This over here are 3 approximations that are using linear functions, which are constant functions, to make rectangles. As I said, you're going to see trapezoid rule. Trapezoid rule is going to cut at an angle, so y equals mx plus b, that's the next step up. And then Simpson's rule is the quadratic approximation. So you will learn those in Calc 2. But for the entire lecture that you see so far, what are the highlights? First off, you can calculate, you can approximate the area under the curve by splitting that area into equal, they don't have to be equal, but it's for convenience we split them into equal. Equal rectangles, right, of the same width delta x, which you can compute with b minus a over n is number of rectangles. And then once you have those strips, you can just go and say height, which is when you compute the function, times the width, which is delta x. You can come up with a rectangle. Now you can have the left side, right, the left hand, as you are working, right, the left hand's right here. So when I put the divisions up, left hand, right hand approximations, so because you will be calculating at those points, or the mid one, right? But then no free lunch, you have to compute these, right? Or what is the value that I'm computing in a function? So, you know, you pick your poison. The important thing here is to realize that your answer, right, will depend on how many, I mean, the precision of your answer will depend on how many rectangles you're computing. The more you do, the more you compute, the better. Now, NJIT has the lab on this kind of stuff, so you are supposed to go and you can write the code in MATLAB, and then you know, use this. So technically, guys, this is, you will see later, integration. This is integration with limits. I mean, not limits, limits. Well, you'll see. Shh. That's it. That's enough. Is there a way to shorten these lengthy expressions here? Because what if I had 15 of these? Right? I'm going to sit there and write those 15? No. I don't want it. We are going to use sigma notation, summation notation, to help us out with these things. So Greek letter sigma, which is capital S, which is equivalent to capital S, which stands for sum, right? So all of that together is going to be used in this notation, and you probably saw this, right? They like to wave with this in movies. If there's supposed to be some complicated math, they always put this in because it's just adding numbers. So obviously, right? That's as complicated as we get, right? If you really carefully look into any movies that have mathematics, you will always find this. And what this means is you're just adding. That's all it is. So let's take a look at summation notation. Summation notation. Whee. So summation notation, this is what it says. First off, we have the symbol for it, right? And this is called sigma. It means add, right? Now, how it works? Well, we put the counter I on the bottom and say I goes from 0 to, let's say, 3, and we put the formula I inside. I is going to take on the values here, and those values are always integer values. So this is 0 plus 1 plus 2 plus 3. Stop at the top number. It's a very simple notation. So this is equal to 6. Summation I starts at 1, ends at 4 of I squared. Okay. That's just going to be 1 squared plus 2 squared plus 3 squared plus 4 squared. You see that variable I is taking on the... So variable I is taking on the values from the counter. Counter goes from 1 to 4. So 1 goes in, becomes 1 squared, and then plus, because it's summation, then it picks up 2 and 3 and 4, and you just go around. So this is going to be 1 plus 4 plus 9 plus 16 for the total of exact 30. Summation of xi when I goes from 0 to 4. Well, now I is just a subscript. This is what we actually need. So I is a subscript, which means this is x0 plus x1 plus x2 plus x3 plus x4. We stop at the top number, and the top number is 4. So I'm just going to start this one because that's the one we need. You can have any function you want that involves these i's. Summation I starts at 0, goes to 3 of 2x raised to the I. So you've seen me I to be the base, I to be the subscript. Now is i's exponent. This is 2x raised to the 0 plus 2x raised to the 1 plus 2x squared plus 2x cubed. Two x to the 0 is 1 plus 2x plus 4x squared plus 8x cubed. And we have a polynomial that was written in compressed form this way. Now, why do we want this? Well, we are going to go to the n, and then we're going to go to infinity. The ones that I showed you so far are all finite. You can have infinite sum, and that's going to go from I starts at 0 or 1 to infinity. Now, if you have this, and let's say I, you're going to have 0 plus 1 plus 2 plus 3 plus 4, going on forever and forever, because you never stop. It goes to infinity. Now, Calc 2 has 2 chapters of that kind of stuff, where you are going to see that certain formulas that you make with this will add to a finite number, and others, right, will go to infinity when you add them. The whole chapter of that stuff, and then the next one with that stuff and the functions. Yes.
Is there a way to increment instead of going up, like go down? So start at a high number.
No. I mean, there is, but you know how high you want to go, so you just do that number minus I, and then decreases, right? So that's the summation notation. Now, you can always factor and do, right, because variable for summation is I, not x. So if you have, let's say, just like ix, let's say, and I goes from 3 to 6, you can kick x out. because the variable is I. Just like when you using the limit for that age goes to 0 for derivatives, you can kick x out because age is the variable in eyes of the limit, and x was just a constant in the eyes of the limit. So the same thing goes here. This x can go in, x can go out. The time when x can't move is if you have x to the I or xi or something like that. Right? Then you can't, because obviously I operates on that x, and you know, they're working together. But in this case, you could do it. And we'll see more uses of this in the next section. So let's take you know, a few minutes, and then we'll do the next section. Bye.